Okay, so the final talk for today will be by Janet Galeano Penaloza, and the title of her talk is Semilinear Cauchy Problem Associated with a p-Adic Non-Local Ultradiffusion Operator. Please, Janet.
Thank you. Thank you so much. So, hello, everyone. Good afternoon. First of all, I would like to thank Professor Wilson Zúñiga and the organizing committee to let me present here this talk. It will be a short talk. All the results in this talk are in an article that published in a joint work with Oscar Francisco Casa Sánchez from Universidad Pedagógica y Tecnológica de Colombia and Leonardo Chacón Cortés from Galeano, also in Colombia. Okay, so here we have the contents of this talk. First of all, I want to mention a short motivation for our work. Then I'm going to define the operator and the symbol we are dealing with. And then we associate the corresponding Markov process, which is indeed a Feller process. And finally, we want to study the semilinear Cauchy problem associated to this operator. So this is the operator that we want to study here. The main important thing is that we can see as a generalization of Typeson operator. So I'm going to define the symbol later. Okay. Lately, p-Adic numbers, and more precisely, the equations of mathematical physics over QPN, have attracted the interest of a large number of researchers in several areas due to their high potential to solve problems of mathematical modeling. We can see, for example, this excellent article where we can find a big overview about some application of p-Adics. The ultrametric nature and its hierarchical structure make of QPN a powerful tool to describe and study some phenomena whose space of states is hierarchically organized. As examples, we have these papers, just to mention a few. We also find some papers that combines theory, this p-Adic theory with biology, cognition, psychology, and behavioral economics models, among others. Also geophysics, just to mention a few. So all these works highlight the need to develop a robust theory of partial differential equations, or for our case, pseudo-differential equations over QPN, similar to the classic theory for the real case or Archimedean case. So we have as a proof the increasing number of published works in this area. So we have these books, just to mention a few, and in these works, the authors dedicated a great part to study these pseudo-differential equations. So we can notice that most of the existence work in this direction are focused on solving linear initial value problems, in several cases associated with the p-Adic heat equation. And the technique used in some of these works consists in verifying that the proposing solution is indeed a solution. So we need some calculations like time derivatives, the application of the operator, and some estimation in order to use the main theorems. Instead of doing some of these calculations, we can use the theory of semigroups. And this is the tool that we have chosen to solve our problem. So in this moment, I'm going to define the symbol of the symbol of the operator, right? So for D1 and D2 natural numbers, we define this symbol. We call it A, D1, D2 to alpha, and we calculate it as this maximum. So it's easy to see that we can express this function as this divided into parts, or we can express it as this sum where this omega function is the characteristic function of the unit ball. For alpha d1 minus n, a positive number, and phi test function, we define the operator d, d1, d2 to alpha by this formula. So we express it in terms of the symbol a, d1, d2 to alpha. But here, this is not a pseudo differential operator. So the main objective of the first part is to describe this operator as a pseudo differential operator. And we have to notice here that if in the case d1 equals d2, then we get a generalization of Tableson operator to a constant, of course, this constant. So, as I said, the goal of this work is to study this operator. We need to write it as a pseudo differential operator, so we need to find its symbol. And then we want to study the Cauchy problem and the Markov process associated to this problem. Now we have to choose the best space for our problem. So we choose this space M lambda with, I'm gonna define it right now. This is the C vector space of all the locally constant functions that satisfy this inequality. This inequality. And for the case lambda 1 and lambda 2 are in this relation, we have these relations between the spaces. And the most important here is that the space of test function is included between all of these spaces. Also, this space includes some functions that are not in the space L1. And the second thing we can notice is that we can define a norm on this space. And with this definition, this is actually a Banach space. So we have some theorems to work in this space. And the third thing that we observe here is that if we choose phi from QPN to our ellipsis function, then phi belongs to this space. So when we were working with the semilinear problem, we want to take the semilinear part ellipsis function because we stay in the same space. So the first thing we can notice here is that the operator d1, d2 to alpha is well defined in this operator. So, and is a linear operator. So this is the first I mean, we choose this space M lambda because the operator is well defined, but also because we can choose the ellipsis function as a semilinear part, and we can solve the problem here in this space. Now, since we are interested in getting an expression for d1, d2 to alpha as a pseudo differential operator, we need the Fourier transform of this symbol. So we started calculating the Fourier transform, and we get to this kind of function. So we define this C, d1, d2 to alpha as like this sum. This definition works for real part of alpha, a positive number, and alpha di different from these values. And this is a regular distribution acting on the test functions. And the main reason to define this distribution is that the Fourier transform of this symbol A is precisely C d1, d2 to minus alpha. So we want to remember that we want to find the symbol of the pseudo-differential operator. So we think at first that this is the symbol, but we need to do more calculations. As example, we have that if D1 equals D2, then this operator is actually the type-Leson operator, as we said at the beginning, and the distribution CDD 2 minus alpha is precisely the multi-dimensional p-adic risk kernel, as we know. For the case that D1 equals 0 and D2 different from 0, then we have the Bessel kernel. And we already know this expression for that kernel. Another examples that we have take is that we can consider more than two numbers. But if the numbers are in this relation, then we notice that this maximum is exactly the maximum. We just need the first one and the last one, and we get our symbol. Also, we can express this maximum as the sum, where the norm, the p-adic norm of each Cj is precisely 1. So that means that all the results that we get here coincide with the known cases. So now we want to study the distribution C, D1, D2. And this distribution has a meromorphic continuation to every complex number alpha, with alpha di different from these values. And how to get this function, this expression, as usual, we sum minus phi in 0 and phi in 0, and we get we calculate the integrals and we get this expression. And also we can notice that this expression have a simple pole in this point with alpha satisfy this equality, and the residue is given by this expression. So we can prove that as distribution, we have the Fourier transform of this this distribution C, D1, D2, 2 minus alpha is precisely the first symbol that we already defined, A, D1, D2, 2 alpha, with some conditions, of course. But this is not the symbol, not yet the symbol of the operator. We need to study a little bit more the symbol A, D1, D2. So we have to do some considerations. For real part of alpha, satisfying this inequality and phi a test function, we have that this distribution acts as a regular distribution, by integration, right? And this distribution has a meromorphic continuation to all complex number alpha with this condition, yeah? And we can find it like this with the same procedure. We have to sum and rest phi in 0 and calculate the integrals. So we continue the study. For real part of alpha satisfying this inequality, we have that when we consider here the symbol with minus alpha, then we get this expression. So here we get the part that we already knew that we have obtained, but there is an additional part here, and we have to include this term for the symbol of the operator. That is the main objective of this first part. So, in summary, if phi is a locally constant function, we can form this convolution, yeah, which is actually an ordinary function of x and is given by this expression. When we put minus alpha, we get this expression with this additional term. And for real part of alpha satisfying these inequalities, then we have this. So we need to include this part in the symbol of the pseudo-differential operator, because remember that remember the definition the definition of the operator D, D1, D2 to alpha. It was, we put A, D1, D2 in the, here, no? So the symbol is precisely this one. C, D1, D2 to alpha in 0 minus C, D1, D2 to alpha in Z. So we have here the expression for this operator as a pseudo differential operator. Remember, but we have to put here the, I mean, how acts the operator. First, the Fourier transform of the function, then the symbol of the operator, and finally the inverse Fourier transform. So the symbol is precise this expression. Now that we have written this operator as a pseudo differential operator, we can do the procedure to solve the equations, the Cauchy problem, and also to study the Markov process or the stochastic process. So next we want to study the Feller process on the space C0 of QPN. I mean, the space of continuous functions that decay at infinity. The first result points out the relation between a negative definite function, I mean this one, this is a negative definite function, and the symbol. And the theorem says that this is a symmetric Levy measure. In fact, we can use, or we can see this part as a particular case of the Levy-Khinchin formula, right? The Levy-Khinchin formula gives us this part. The Levy-Khinchin formula is bigger than that, but for our case, we just get the integral part. So, like this function is a negative definite function, its Fourier transform defines or determines a convolution semigroup, and we call it zeta t. And this is a convolution semigroup on QPN. Okay. So since for this function phi that is negative definite, if we calculate phi in 0, that's equal 0. So that semigroup, that semigroup zeta t is actually a probability measure. So here we have some important properties of the function zeta. First, zeta is a non-negative function. The integral of the whole space equals 1, which agree with the probability properties. Here we have the property, the semigroup property, and also we have this limit. When t goes to 0, this zeta function goes to delta function. Now, for rho in this interval, it is possible to find a bounded operator t of norm less than or equal to 1. We define t by this convolution. This operator t is called the convolution operator induced by zeta t, and it satisfies some properties. First, t is translation invariant, and t is sub-Markovian. And we can remember that a family of operators, of bounded operators on L row of QPN is called a contraction semigroup if satisfied two conditions. The first one, the norm of the operator is less or equal than 1, we have that. And second condition, they have the property of semigroup. The contraction semigroup that we have here, we can conclude that this family of operator is a contraction semigroup, and all the operators are translation invariant, sub-Markovian, and they are strongly continuous. Now we set the space of continuous function. This is the definition. We have some decay at infinity. And we recall that with the infinity norm, this space is actually a Banach space. So we work this part in this space. Now we need to remember some definitions. We said that strongly continuous contraction semigroup over C0 of QPN, for which all operators PT are positive, I mean satisfy this implication, is called a Feller semigroup on QPN. So that's the condition we have to prove. Now, for any fixed T, positive or zero, we define the operator PT by this formula. For T, a positive number, we define as this convolution. And for T equals 0 is like identity. And this operator is bounded. And we can prove that since zeta T belongs to L1 and phi is bounded, then we have that this convolution is actually continuous. And finally, we can prove that the contraction semigroup PT is a translation invariant Feller semigroup on QPN. Now, we will denote by B of QPN and the sigma algebra of the Borel sets of QPN. And we can define this measure over B. I mean, we get the definition and then we can prove or observe that this is actually a measure over B. How to define this PT? The convolution between the zeta function and the characteristic function of the set for T, a positive number, and just the characteristic function for T equals 0. So we have that PT is positive or 0 for all T positive or 0. And we have this expression here in terms of the symbol of the operator, right? So we can observe that PT is actually a measure over the sigma, this sigma algebra. Finally, we prove that PT is actually the normal transition of some strong Markov process, which is bounded, right continuous, and has no discontinuities other than jumps. First, we need to remember that a Markov transition function satisfies these 4 conditions, right? We have here that PT is a non-negative measure on the sigma algebra. All these measures are Borel measurable functions. And also we have the Chapman-Kolmogorov equation. This condition can be taught as follows. The value of PTXE is the transition probability that a particle starting at position X will be found in the set E at time T. And the Chapman-Kolmogorov equation says that the transition from the position X to the set E in the time T plus S is composed of a transition from X to some position Y in time T, followed by a transition from Y to the set E in the remaining time S. This is the last probability. And this depends only on Y. And we need to remember 2 more definitions. We said that transition function is normal if satisfy this condition. We can express this like this limit, and this limit equals 1 for all x in QPN. And we said that a Markov transition function on QPN is said to be uniformly stochastic continuous on QPN if we have this condition. For each epsilon positive number at each compact E subset of QPN, this limit equals 0. So as a consequence of the fact that capital P sub T is a translation invariant Feller semigroup, we can conclude that this function, lowercase p sub t, is a uniformly stochastic continuous C0 transition on QPN, and satisfy that for each S positive number and each compact E subset of QPN, this limit is precisely 0. And therefore, we have this result. The function pt is the normal transition function of some strong Markov process, which is bounded right continuous and has no discontinuities other than jumps. Okay, so with this theorem, we finish the stochastic part for same. And the other thing that we proposed in this work was to study the semilinear Cauchy problem. And as I said, we can consider phi f. This is a semilinear Cauchy problem, not a non-homogeneous problem, right? So we choose this function f from R to R, a Lipschitz function. And the reason to do that is because we already know that this operator is well defined in this space, and all the norms and the estimations we can obtain in that space. So we studied this problem, and the first thing that we can observe is that the operator satisfies a Lipschitz inequality. So if we take U and B belonging to M lambda, and L is the parameter of local constancy of U minus V, then we can prove that this difference is bounded by this expression. So this is a Lipschitz inequality. Now we want to define some the final operator. In order to study the Cauchy problem, we define this operator. So we are dealing with this part because we want to use the Cauchy-Lipschitz-Picard theorem. And in that theorem, we have this partial derivative with respect to time and an operator. So we define this operator, F, capital F, as lowercase f in U minus the operator applied in U. So now, again, if we choose f a Lipschitz function, then this operator is also Lipschitz, because we can do this, we can bound this difference for this expression. So we are in the conditions for the Cauchy-Lipschitz-Picard. I mean, we need to write it in terms of the norm of this space, because this is a Banach space, then we can use that theorem. So for the Cauchy-Lipschitz-Picard theorem, if we put the initial datum in this space, and we want to study this problem with this operator that satisfies the Lipschitz inequality, we can conclude that there is a unique solution U in this space, which is solution of this problem, right? So we have proved this theorem. This Cauchy problem has a unique solution. The solution belongs to this space, C1 of 0t and M lambda, And the conditions for that is that the function u0, I mean the initial datum, is in the space m lambda. And the other condition is that the function f from R to R is a Lipschitz function. And we already know that for that reason, I mean, if f belongs, I mean, if f is a Lipschitz function, then f belongs to m lambda. So this is the main theorem we have to prove. We wanted to prove. Here, these are the references we have used for this work. The first is the book from Berg and Force, Potential Theory on Locally Compact Abelian Groups, and all the theory about semigroups. We use that book for that part. For the Feller semigroups, we use this book from Kazuaki, and this is the article that we have published the last year where we have all these results. Thank you.
Okay, thank you, Janet. Any questions?
Yes, I have a comment, Janet. Could you please show us the definition of the symbol? It's probably in the first page of your presentation. The one, yes. It seems to me that you can also consider, I mean, that your results can be applied to the case in which instead of the maximum, you have the minimum. Why? Because in the case of maximum, the behavior at infinity is controlled by the largest number between the 1 and the 2. If you now use the minimum, then this condition switches.
Interesting. We haven't thought about that, but
that's important, because then if you have, it seems to me that the minimum, if you replace the maximum by the minimum, your results are also valid. But then you have now, you can construct more general symbols, because the set of negative definite functions form a cone. Then you can take linear combinations of functions involving max and min, and now you have an infinite family, a very large family of symbols. You see?
We will work on that. Thank you.
Okay.
Any other questions?
I have a question. Do you hear me?
Yeah, please.
Yeah. So please show the slide with the Lipschitz functions. Will you please?
At the end?
Yes, at the very end, when you are speaking about Lipschitz functions, because you are speaking about Lipschitz functions which are defined. This is real Lipschitz functions. No, not this slide. The next one. The next one, please. Your main theorem. Where is your main theorem? It was the last slide, maybe, right? Yeah, that's one. Theorem 11. So this is only for function. I just wonder, could the theorem have a p-Adic counterpart? So what happened if, for example, I would like to get somewhat looking like that theorem, but where f is one Lipschitz safe function, but where is r, there is not r but zp. The ring of p-Adic integers. The ring of p-Adic integers is a compact set, you know. So, any suggestions? Could it be? Could it have a counterpart?
I'm sorry. Can you repeat the question, please? My English.
The question is here. F is a function which define the real numbers and evaluate whose range and domain are real numbers, right? Yeah,
right.
The function, right? I'm just wondering, could this theorem be true, or in somewhat could this theorem have a counterpart, a sort of counterpart, where f is not f is a Lipschitz function, maybe with coefficient 1, but whose domain and range are p-adic integers? Just your opinion. Could it be so or not? In somewhat, maybe some reasonable restrictions, under some reasonable restrictions.
I haven't thought about that. We just try to consider not the non-homogeneous problem, but the semi-linear. So I didn't know the answer.
Because yeah, I understand, but just your opinion. Because the operator, you can define these operators on the p-adic integer. They exist. Because this would be actually this would be interesting personally for me. That's why I'm asking that problem, that question. So you don't know, okay?
No,
just,
let me make a comment with respect to the question of Vladimir. It is necessary to do a lot of modification, Vladimir. For instance, the operator d alpha is an operator that acts on functions from the p-Adics to the real number. So the first step to answer your question is to change that operator. So now we need an operator acting on functions defined from the QP into QP. So this is the first modification that we need to do. Then the problem, there is an additional problem, Vladimir. In the demonstration of Theorem 11, the authors use semi-group theory. And this theory is only valid when the time is real. We don't have a general theory for semi-groups with p-adic time. This is a difficult problem. But I think that if we replace d alpha for some nice operator acting on functions from the p-adics into p-adics, perhaps it is possible to say something. But it is a difficult question in the framework that you are asking, because in the framework that you are asking, you don't have semi-group theory.
You see, because why I'm asking this question, because you see in some my studies, the p-adic time emerges very naturally.
Yes.
P-adic time, not real time, but p-adic time. So I just wonder, maybe there could be a sum of counterpart of this result. It would be very interesting for me. And I understand that the operator must be from. Mostly, I'm of course interested from p-adic integers to p-adic integers, but from QP to QP is also be very interesting. So for me, that setting of a problem deserves some investigation, maybe. Okay. Okay, thank you. Yes, I got the answer.
Okay. Any other questions? Or comments? Okay. Thank you again, Janice.
Thank you.
Okay, so don't forget that tomorrow we have